Now that we've had a chance to work some more with properties of exponents, we're going to go the opposite direction for the next 4 days, working with square root expressions. And so for those of you who are wondering why we did 1-5 before 1-3, simply because 1-3 is a little bit more challenging than 1-5, so we figured we'd give you a comfort base before we got into more challenging work. We dealt with exponential form, and now we're going to talk about radical form, which is where you have a square root where n is that index. It's still that n from before, it's that index, so we have the radical sign and the radicand, which is what is inside the square root. Before we move on to some actual examples, I want to review our perfects. And what we mean by that is our perfect squares, which you know. I do expect you to know through 14. 1 squared 1, 2 squared 4, you can read the rest. Then we also have the perfect cubes. I really would like you to know through 6 cubed. Once we get above that, we can start focusing on looking at our calculators. We also have perfect fourths, which I would like you to know at least through 5, preferably 6. And then our perfect fifths, which I would like you to know the first 3. As you know, you can use a calculator, so therefore if you do not know these memorized by heart, you can put them in the calculator, but it is nice and handy to have them memorized, so that way you don't have to refer to a calculator. Let's try a few examples. So our first one, we've got the square root of 16, which we all know is plus and minus 4. We're going to focus mostly on the positive ones, so I won't worry too much about the plus and minus, but know if there is a negative up front, I am looking for that negative piece. With these, basically it comes out to separating into perfect and non-perfect factors. I did A first because I know that's a perfect square, and then once you've separated it, then we're going to take the root of the perfect factors, leaving the non-perfect factors underneath the radical sign. So looking at B, I see when I have 135, I'm trying to think what goes into it. I know that 4 doesn't work. I know that 9 doesn't work. Actually, 9 does work. I take that back. So knowing that 9 works, we know it is 9 times, and then we have to figure out what 9 goes into it. 9 goes into 13 once, there's 4 left over. 9 goes into 45 5 times, so we know it is 9 times 15. So then we take the square root of 9, which is 3. 15 is 5 times 3, which neither are perfect, so we leave 15 inside the radical. Looking at it with when we have some variables in the mix, I know that I'm going to need my negative, and I know that x to the 7th is not a perfect square, but if I have an even exponent, that will be, so we can break it down into x to the 6th times x. If you would like, you can break x to the 6th and the x squared times x squared times x squared and square root it that way. But I don't need to do that. I have the negative out front. The square root of x to the 6th is x to the 3rd, because just like when you take a power to a power, you multiply the exponents. When you square root a power, you divide the exponent inside the square root by the index, which in our case is 2. And then we have the square root of x still left inside. Let's move on to something a little more complicated that has both numbers and variables there. I know it's not divisible by 4 because it's odd. I know that if it's not divisible by 9, because if I take 245 and add 5, 4, and 9, and 2, I get 11. And then I look and say, all right, is it 16? Well, if I put a 16 in, 16 is not going to work, because we're going to end up with numbers that don't end in 5. So then I think 25. 25 does not work. I know that 4, 9, 16, and 25 don't work. I look and I say, well, I know 36 is not going to work for the same reason that 4 and 9 don't work, because 9 times 4 is 36. So I'm going to try in a calculator 245 divided by 49. And what do you know? 245 divided by 49 is going to be 5. So I have 49 times 5. X squared is a perfect square. So is y to the 4th. Z is not. So then I can square root. Square root of 49 is 7. Square root of x squared is x. I left the 5 because I know it's not a perfect square. Square root of y to the 4th is y squared. And the rest of what's inside is non-perfect, so I have 5z. And that is my solution. Looking at example E. Example E, I see I have a to the 9th, which is not a perfect square, so I'm going to break that into a to the 8th times a. And b to the 3rd is not, so I'm going to break that into b to the 2nd times b. If you haven't noticed, I want, for perfect squares, I want even exponents, and I have a c left over. So then I square root a to the 8th, which is a to the 4th. I square root b to the 2nd, which is b. And the rest of what's inside is a non-perfect square, which is a, b, c. For our last one, this one's a little bit trickier. We have here, I notice, a cube root. In that case, we want variables to powers that are divisible by 3. And when I look here, I see that 27 is a perfect cube. Well, that's 3, because 3 times 3 times 3 is 27. A to the 6th, if I take this and take the cube root of a to the 6th, is really a to the 6th divided by 3 power. So I know it's a squared. And b, the cube root of b to the 12th, is really b to the 12th divided by 3, 12 divided by 3 power, which is b to the 4th. So therefore, b to the 3a squared, b to the 4th is my final answer. I have here 5 U-Try problems that I want you to go ahead and simplify these down as far as you can. Write your summaries and bring your questions to class tomorrow.